phosphor that takes the X-rays, converts to light. It goes to the photocathode that takes the light X-rays, convert it to electrons. The electrons go across. Because this input and photocathode are curved, the electrons on the outer edges will come across and cross at the focal point and the output phosphor. We do have a glass envelope or an envelope of some sort that creates a vacuum just so that these electrons will not hit air molecules and be diverted. We want them to go from the photocathode to the output phosphor. We do have a metal tube around it, and that's more for structural support as opposed to an X-ray tube that's to absorb any radiation going out besides the port. So this outer metal tube is a little bit different than what we have for an X-ray tube. So what makes the image brighter? There are three things basically. Remember the minification gain. All the light from the output phosphor goes onto the input phosphor to the output phosphor. Let's look at that real quick.
Brightness gain.
Yes. Did what now?
Brightness gain, conversion.
Brightness gain and the flux gain. The flux gain is where you have, let me show you the picture. This is the flux gain where you have a multiplication of one X-ray photon produces more light photons, which produce more electrons. So that is called the flux gain. And then the brightness gain is the flux gain plus or times the minification gain. What does it mean? Let me ask you this. What input phosphor will give you the highest minification gain? A 12-inch or a 9-inch or a 6-inch phosphor? Which would give you the highest minification gain? You're taking the light from a 12-inch. Okay, let's think about it. You're taking the light from a 12-inch input phosphor onto a 1-inch output. Or you're taking the light from a 9-inch to a 1-inch. Or you're taking it from a 6-inch. So it's the larger one. Now, let's go with which one will give you the most magnified image. Now, that's the smallest one. Okay. So for brightness, for minification gain, that means that's making the image brighter. And which one of those three will make it the brighter is the larger one. Which one magnifies it more is the smaller one. So make sure you read about that and understand that. We had the conversion factor. Remember that. That is input, radiation input to light output. It has two terms, big name, veiling glare. We talked about pincushion effect, and then we talked about the multi-field tubes and what happens when we did that. We went into the lab and I showed you the different multi-field tubes and how it magnified the image. And so what happens when we go into the mag mode? What happens to the focal point? It moves further away from what? Or closer to, right? In the mag mode, the focal point will cross closer to the input phosphor and further away from the output phosphor, right? Remember that? Okay, that makes the image spread out over a larger area. So we only have a 1-inch input phosphor. We're not capturing all those electrons, electrons. So the image appears dimmer. Okay, so the machine kicks up the MA and the KV to make it bright again. So when we're in the mag mode, remember we looked at the screen and we saw the milligray up in the corner. And what happened when we went to the mag mode each time?
It went higher.
It went higher. And that's because the machine is kicking up the MA to make it brighter because we lost the brightness when we magnified. And here's a picture. Just remember this one. This is normal. You're in normal 12-inch mode as an example, and you see all the anatomy on the output phosphor. Then when we magnify, go into mag mode, the focal point crosses sooner, the image spreads out further. Okay, that's why we see the magnified image here, but we're losing these electrons to hit the output phosphor. So the output phosphor is going to be dimmer, less bright. And so the MA picks up to compensate for this loss here. So that's why it increases patient exposure. I have a clicker. I don't know if I keep coming. Oh, here it is. Okay, and this is where we are now, automatic brightness control. This is when the machine automatically adjusts for that decrease in brightness. Now, what is the MA? When we were doing our lab experiment or demonstration, I had you go out there and look, and it was like 1.9 or something like that. It's usually anywhere from 3 to 5 MA, or it can be anywhere from 1 to 5. It's not going to go over 5, not legally anyway. It can go over, let me rephrase it. It can go over 5. Typically, it doesn't. Our Pixie wasn't a real human, and it didn't have barium in there, so that kept the MA pretty low. If it was a real person with barium in them, the MA would be kicked up a little bit higher. Okay. The kV that we use is just for any body part that we normally use it for. So like if you're doing a barium study, it's going to be 120 or whatever. If it's going to be an iodinated contrast study, it would be more like in the 70 to 80 kV range. So you adjust the kV according to the study that you're doing, just like you would for a regular x-ray. Usually radiographic kV and fluoro kV are separate, so when we're fluoroing, we have those fluoro exposures, and then when we kick into radiographic mode, when they go to take a radiograph, an image, a digital image, it'll kick over into radiographic mode, meaning radiographic MA and kV. What is radiographic MA? I mean, what numbers are we looking at there? Fluoro MA is 3 to 5. What do we use for radiographic MA? What do you do for a hand?
Like around 1? Or?
Not 1. This is why I ask, because how easy you forget with your new digital equipment. 100 or 200 or 300.
I'm thinking about mass.
Yeah, everyone thinks about mass. Yeah, you're thinking mass. You're not thinking MA in time and kV. So my question was, what is the MA that you use in radiography? And that's in your, 50, 100, 200, etc. Okay? So fluoro MA is anywhere from like 3 to 5. So very, very low compared to radiography, routine radiography. So there are different ways we can look at the image. I have not talked to you about this, right? Okay. I had lecture on Tuesday, so I forget what I told you now. So there are different ways to look at the image. One way you will never ever see, and I've only seen it once, is the optical, looking at mirrors, looking at the image reflected onto a mirror. I'll show you that in a second. And then after that, I've always seen it on a TV monitor. Well, now we're not doing TV monitors, we're doing computer monitors, so that's the difference there. We did cinefluorography, and this is where you take the image and put it on movie film, like literally movie film. What is it, 35 millimeter movie film. Spot film cassettes, this is like movie film. This is like movie film, but it is bigger. The image is on, well, it's just of a spine and abdomen, but this is 105 millimeter. Okay, and then I'm sorry, that's the photo spot camera. This is the photo spot camera, and then spot film cassettes is just like the film screen cassettes. We actually took X-rays with a cassette with screens in it with a piece of film. So these are different ways that we captured the image. Probably one other way that I don't have up there, it worked with the TV monitor, and that was VHS recordings. We could videotape the image off the TV monitor. I know, I just remember those days. Okay, so this is kind of the setup. Here you have your II tube in this particular room, and sometimes it would be quite the array of stuff coming off of the II tower. Ours is just the II tower in our back room, and it's so small and neat and compact, and that is just not how I grew up with it. Here's a cine camera. If we had cinefluorography in that particular room, I'll talk more about this, but this would be an angiography. in angiography, they use semifluorography. The spot film camera, there's spot film cassettes, spot film camera. Okay, the other name for spot film camera is photo spot camera. Okay, what I showed you just a second ago. They're the same thing. Here is a TV camera tube. I remember we used to have this in our room. I would unhook it and point it towards the students, and we would see you on our TV monitor. So it's just like a regular camera. Guess what the opening of that camera is? It's just like, you know, the old movie cameras, right? 1 inch in diameter. It would sit right there on top of the output phosphor, and then hooked up to a TV monitor, or now we have a computer monitor. So again, this is out of your textbook. Spot film camera, photo spot camera, same thing. Cine camera. You had coupling optics in here. And I'll show you that in a second. You had to direct. Here's the output phosphor. You have to direct the beam where you want it to go. Do you want it to go to the spot film camera? Do you want to go to the cine camera? Do you want it to go to the TV camera? Did you want it to go to this and that? So there were optics in there that would, mirrors that would, beam splitters, that would split the beam up and send it to whatever device it needed to go to. Here again is a TV camera tube right there. We used to have to learn about that. Orthicon, Plumicon, Vidicon tubes, but we don't now. And certainly, you know what, we've replaced that. Do you remember the CCD, charge coupling device that we learned about in last semester? Okay, so in here are the beam splitting devices there. So this is kind of what it looks like on the inside. Here's another one. Here are the mirror optics. So it can split the beam. Some of it can go here to the spot film camera. The rest of it will go to the TV camera tube.
This was all like, this was all analog signal, is that right?
Yes.
All right.
Yes. Analog signal. Okay, so the optics, I got to see this one time. It was right before I die, I'm going to remember this because it was just so amazing. Okay, so remember back in the day, the radiologist would look at just the flat screen, okay, glowing. So then they added the image intensifying tube so that they could make the image brighter, so we could use our what type of vision? No, they were using peripheral here.
We could use our cones.
We want to use our cones. Peripheral rods and daylight vision are the cones. So now we have to be able to see the image. Well, not that this was before TV, but maybe. The image would come out here and hit a mirror. Look at this. It would hit a mirror, and that reflection would be reflected onto this mirror, and it's angled a certain way to hit this mirror, and that's angled a certain way to hit this mirror. This is the mirror the radiologist would manipulate. And what does this mirror look like? It looks like you could buy it from Target. It's like a makeup mirror, just a round mirror. But unlike the $10 mirror you buy at Target, this is much higher grade, very good imaging. So it's not like what you would see now. It's very high quality mirrors. And so the doctor, the radiologist, would move the tube back and forth, and this hand was always on the mirror. Now this was the one room that we had when I was first in x-ray school. That room, and you know what I'm talking about, that nobody likes. That old room, that cantankerous old room, is eventually going to be replaced, but it hasn't yet. And so I had one doctor who had no problem working in there, so I'm working with them. And it's boring. The lights dim because he's trying to see the image off the mirror. The lights are dimmer than normal. And what am I doing? Making sure the patient's okay, getting the barium, thinking about lunch. And so the doctor turns to me and he goes, "Do you want to see?" Yeah, okay. So I come over here, and I know that he has to, and I'm shorter, so I have to angle the mirror differently as I'm looking at it. And I could not capture that image coming off of this one. I mean, he's fluorine for me, right? There's a patient on the table. And he's like, "Do you see it? Do you see it?" And I'm looking, and he knew. immediately when I saw it because I did the, you know, and it was an upper GI, so the stomach was like a dark green, the air was a light green. It was just different shades of that green color. You know, when you saw the screen fluorescent in the room, that green, okay, it's just different shades of green. It was really bizarre. I'm used to black and white, and so shades of gray, so to see, you know, dark green, light green, and different shades of green, it was pretty cool. I just got that long before he took off, you know, got off the fluoro with it. So, but there was a technique to that. And so if you're not adept at that, doctors back in that day, they had to be pretty good at that, because if you weren't, what happened to the patient exposure?
Overexposing it.
Yeah, it would increase your exposure because the doctor's trying to capture that image, you know, so there was quite a talent to it. And of course, you'll never see that ever, ever, ever. I was just lucky to see it that one time, and then it was gone. So again, the field of view, FOV, the field of view was small. Only one person can see. The patient can't, you know, the patient's just laying there doing what the doctor says. I can't see. I have to take overheads afterwards. I don't know if the stomach's long and J-shaped. I don't know if it's high. I don't know what pathology is being seen to maybe make any adjustments. And then of course, every time that image is reflected from one mirror to the next, the brightness is lost. Some brightness is lost due to the reflection. And of course, the advantage is that it's less expensive than a TV monitor or anything else that might be used. Okay, so let's move forward to the TV monitor. This was expensive, of course, but many advantages to this. The output is coupled. Now here I have to a CCD. At the time, back then, it was a TV camera tube. Okay, more people can see it. Can't you do this on your computer monitor? Can't you adjust your brightness and contrast to an extent? So that was nice. How do we adjust our brightness in fluoro? How is it adjusted? If I want the image to glow brighter in fluoro right now, today, what would I have to do? As you would with any screen. How do we make screens glow brighter? Yes, absolutely. More X-rays, more MA, more KV. That's what makes the screen glow brighter. But if I can adjust the TV monitor or the computer monitor a little bit to help with that brightness, I don't have to do it with radiation. So that was, it doesn't give you a lot of leeway. It's not a lot of brightness or whatever, but it helps. So there's a little, so this is a big deal. And then, of course, with the TV monitor, we had the recording capabilities, as I said, like with the VHS tape, if that's what we wanted to use with that. So, spot film cassettes. Now, these are what I'm talking about. These are like X-ray cassettes that are used. This is where, this is what I talked to you about when we were in the room about putting the cassette in from the front, and then taking an X-ray, and then take the cassette out, and you can process it to get your image. So that every time the doctor takes a spot film cassette image, the tube, so the doctor's fluoroing, sees something on the monitor that they want to record, to take an image of, and we call that a spot film, take a spot of that. And so they push a switch on the fluoro, and it goes from fluoro mode to radiographic mode, takes the image, and then goes back to fluoro mode. And then we take the cassette and process it. Now we can do that with, I know, I think you were saying that you do that at your facility, right, Miss Evelyn? With the CR cassettes, right? And that's that method of taking an image. With digital imaging, we do take images just like that, except now they're digitally recorded and not on a spot film cassette. So it takes, and the reason it increases patient dose is because you're using fluoro. Now think about this, you're using fluoro, now you've got that exposure, then you switch into radiographic mode and take a radiograph. So there's that exposure. Okay, then you go back to fluoro. So that's what we're saying, that this is why it increases patient dose. It takes 1 or 2 seconds to get in place. So remember, the cassette is stored in the back of the tube or the tower, and when the doctor's ready, it slides forward. They take their image. They can do multiple images on one cassette if they want to. And then when they're done with that image, it goes to the back and waits until they want to take another one. They might do multiple. Spits it out. We put a new one in. So it takes like a second or two to get into place. Not a big deal, but that is a delay. So this is kind of what I worked with. And Miss Evelyn, I don't know if yours probably doesn't look this heavy.
Don't be surprised.
It's pretty close. I'll have to come by and see yours. Okay, so let me just orient you a little bit. Okay, here's the table. Do you see this right here? That's your switch to turn the table up or down. So think about what's in our back room that you saw last week and what's here. So we still have that. Here is the opening. Remember I told you there was an opening, and that's where you could put the cassette in. Remember I told you to put the cassette in upside down. Where's the fluoro tube? It's down here. So you have to put it in upside down there. And it goes to the back of the tower once you put it in, sits in the lead-lined area until the doctor is ready. They push a button and it slides forward right under the II tube. So this here is showing the spot film, not cassette, but camera. This is spot film cassette, this is spot film camera. So this is where we're taking the 105 millimeter big film. The cine camera is not on here right now. The cine camera might be on this side, and that's the little movie film. Okay. So I don't know. I can't remember what this is. Could be the TV camera tube would be here. This might be some controls, the beam splitting device, some of the other controls for the spot film camera maybe. Okay, look how big that is. In our back room, you're only looking at this. You've got all this equipment and maybe even more. And so there are latches here that we would unlatch. This was suspended from the ceiling on wires, and so we would unlatch it and kind of come up a little bit, and then we would move it out of the way towards the end, towards the end of the room, and take our regular X-rays, because we could not get an overhead X-ray tube around all this equipment. So we would have to unlock it. Now this part would stay. We just push it back away from the tube like we do in our room. So very heavy equipment, but that's kind of the setup with it. A lot of stuff on there. So photo spot camera, again, this is what I'm talking about, the spot film camera. Okay, this was less patient exposure. Oh my gosh, I remember when this was developed. And our radiologists loved it, because think about it, every time they wanted to take a spot film of anything, they had to take an X-ray. And that just added to the patient's exposure and to the time of the study. And there were some that wouldn't take just one or two. There were some that would take a lot. They're documenting everything. And so that adds to patient exposure, adds to the exam time, which does the same thing. So then now this is developed. This image right here is taken off the TV monitor. It's not an X-ray. This is taken from the TV monitor. So no extra radiation was used to get this image. But it came from the TV monitor, which is the worst in resolution. Okay, so the resolution is what we're taking on. So the resolution is not the best on here, but no extra patient exposure. I had doctors that would have just rolls of this after an exam. And then they would go through, and what do you do with these? Where did these go? In the patient's, folder? And the doctor would go, I want that image, not that one, or that one, but that one I want. And then they would go, yeah, I want that one. And it would be like, oh my gosh. And so we would have to, we went through several steps with these. We laminated them because they would, patients' jackets, we were not used to that. You know how you have your jackets in the X-ray room to keep your stuff in? Okay, that's what patients had for their films. And there would be patients with 3 or 4 of those jackets of all the studies that they'd had. And so you can't just put that in there, because what study does it go to? Is it the upper GI? Is it the first BE or the second BE they had from last year? So you had to, you know, people had to look at this. So we laminated it. So we would do like 5 in a strip, or however long that jacket was, and we would do 2 at a time. And we had a laminating machine, and we'd feed them through there. We'd cut them, put 2 in there, laminate it, cut that, put it in the folder, laminate the next 2. I mean, so we're back there after the exam doing lamination. So then what developed after that was these came in single sheets. Instead of a roll, it came in little sheets. And so then they made a plastic thing with pockets. So you could put them in the pockets and then put it into the folder. And then inevitably they would still get lost, and so that didn't last terribly long. But it did reduce patient exposure, so that was a good thing about that. Less patient exposure, no interruption. I mean, like I said, the doctors were like, you can just hear that thing just going. Why don't we just record it? Why don't we record the whole exam? That's not spot films anymore. That's just recording the whole exam. And then again, no additional heat load, which is not something I talked about. But again, going into radiographic mode with those cassettes would certainly add more heat onto the X-rays, or onto the tube. So again, this is a little bit better picture. That's where the spot film device. Now remember, I told you I call this the front end. You think this looks old? The one I worked with when I was first starting school, I'd go to the back and we loaded them. Remember me telling you we loaded them in the back? So I went through all that. Okay, so CT fluorography is mainly used for cardiac studies. And this is movie film. So this is like your spot film camera, but it's much smaller, of course. It's really 35, I think it's 35, maybe 17 millimeter film. So very, very small. And this was done using radiation. Okay, right? This image here was taken off the TV monitor. The movie film used radiation to make those images on each little frame of the movie film. Okay? The reason this was done for cardiac studies, if you've ever seen one, has anyone done a rotation yet, or maybe a day in interventional radiography? Okay. The contrast media, especially around the heart, they have to pressure inject the contrast media during these angiographic studies, because once the contrast media gets into the bloodstream, it starts diluting, and then by the time, you know, they put the catheter through the femoral artery, it goes up the aorta, maybe to the level of the kidneys, maybe the aortic arch, for the carotids, for cerebral, or maybe the heart for a coronary angiogram. And so they pressure inject with a machine. You can't push it with your hand. It's not enough pressure. And it lasts that long. So I've seen studies where you see the contrast media go around the heart, and it's done. It goes just like that. It's over. It's like, what just happened? And they replay it over and over again, and in slow motion just to see. But they do it in movie film. Now, let me tell you, the resolution on that was exquisite. You're using radiation. Radiation on film is the gold standard so far as resolution is concerned. So when you're doing something, especially like a coronary angiogram, you want the best resolution possible. So they would use the movie film. You can only imagine the dose for each frame was a certain amount. So that if the doctor used more frames, more radiation. So now with the patient exposure, the synchronization comes from the X-ray pulse, X-ray shooting to the frame, to each frame as it comes through. The framing frequency, are we doing 10 frames per second? You know, 1 frame per second? What is the framing frequency? What would you think if I said, as the framing frequency increases, what happens to patient exposure?
Increases?
It increases, absolutely. And then the F number of the camera lens, meaning how much light is being let, you know. So these, you know, nothing that, I don't have anything on your test about this. It's just kind of explaining how that cine-fluorography worked. And we could not put cine film in the regular processor. We could not put the little tiny movie film through a processor. We could this, but not the movie film. So we had special processors that we used to develop that. And it would be in the dark room, and you would be in there for quite some time developing that. So you had to have the reel-to-reel. Now, how do you look at movie film? Have you ever had the old movies?
On a screen like that?
Yeah, on a projector and the reel-to-reel. So you had to feed it through the projector. So I remember we had for our cardiologist, because you had the radiologist in there performing the exam, the interventional radiologist, but